Hello and welcome to Data Science in Industry vlog. Today I would like to continue the topic from the previous video. As you remember, in the previous video we was discussing the control system. In particular, we was answering the question, what is the distributed control system? I also explained to you why it is so crucial to understand how the control system operates, what are the algorithms that makes the brain of the plant or the factory. Really need to understand those algorithms because they are part of the process that we are modeling. We need to understand them because we need to integrate with the control system, and those algorithms will be a part of our decision path. So the first decision is to AI algorithm, but then that this decision is implemented, is sent to devices through the control layer. Today I would like to discuss with you those algorithms, starting from the closed loop. We will discuss what is the PID controller and other interesting combinations of typical algorithms used in the control system that are executed in the memory of the controller, and we need to be aware of those algorithms. Maybe we can even tune them, and for sure, if we will send the decisions to the plant, to the factory, maybe automatically we will use those algorithms. So let's start. First of all, I would like to mention the fact that processes in industry are characterized by some dynamics. Usually it's a transport delay and first or second order inertia. So it means if I change the input, my control signal, right, my device load, I open the valve, I will push more air, I will change the flow of the water, etc., etc. I will not see the instant reaction of the process outputs. Usually I will wait a few seconds, tens of seconds, hundreds of seconds, minutes or hours, even days, depending on the system, before I see that the output starts to change. Then this change will usually not be instant as well. It will take time to go from the initial value to the end value, right? And this transition is usually characterized, is related with the inertia of the system. So let's take the example. If I'm sitting in the room and I have the radiator in my room, let's say I'm sitting 2 meters from this radiator. If I change the input, so I will change the valve associated with the radiator, I will open it. So it was closed, then I will open it. I will not see the instant reaction of the temperature or of the sensor that I have in my hand, right? First of all, I will have to wait a few minutes, maybe, all right, to see that the temperature starts to rise. It will not change immediately from, let's say, 16 centigrades to, 22 centigrades. I will have to wait a bit. There will be some transition. Yeah? So we'll start with 16 centigrades, then we'll have 70, 18, 18.7, 19.1, etc., etc. We will see, let's say, this kind of a transition before we reach the new steady state, new level of temperature. Let's take another example. If we have a power plant and power boiler, if I increase the set point for oxygen, I will push more air to the combustion chamber. after a while I will see that the NOx emission measured on the stack, let's say, is rising because there are higher temperature, higher NOx are produced. So I will wait, depending on the boiler size, a few minutes up to, I don't know, half an hour to see that the reaction is starting. And then this transition will be characterized by inertia. So we'll see that the NOx emission is increasing and then is settling on the new level, in the new steady state. Usually this transition is also smoother. Here you can see the system that consists of delay and the first order block, the first order inertia. And we have to keep this in mind because this is a challenge for the control system. This inertia, this transport delay, because if we send our decision to the control system, we will not see the instant feedback, right? We will not see the instant reaction. If the world would be so nice that everything is instant, then control systems would be very, very simple, because you can add, it would be not a challenge to reach the desired level of NOx emission or desired level of temperature in this room. But because of this process dynamics, some useful algorithms are needed to help to reach the desired values of the parameters in our factory or in our plant. I will start the discussion about the algorithms from the open loop control. This is the simplest approach. So we have a plant, right? We are measuring some output. I know the temperature, the flow, the pressure. And we have a controller. This controller sends the control signal to the plant. So this plant has some inputs, devices, right? That actuators that can be used that affects the industrial process. In our case, from our example from this room, I have the plant is the radiator and it has a valve. This is the continuous valve, so I can close it, open it, but also I can set it to 60% or 20%, right? So my control signal would be the valve opening level. And I have some demand value. In case of the room, I would like to have, 22 centigrades in my room. This is the comfortable temperature, or 21, depending who you will ask. So what we can do is we can try to create a model that translates the demand value into control signal. If I want to have 22, I should open the valve to 80%. If I would like to have 20 centigrades, I should open the valve to 30%. If I would like to have 12 centigrades, I should close the valve. Such a characteristic. This is the simplest approach. Such approach is called open loop control. As you probably feel, it has some important drawbacks, important disadvantages. Because what if someone opens the window? I have a window here. If I open the window, now it's 0 centigrades outside. It will have an effect on the temperature in the room, right? What if somebody opens the door? Or maybe the room will be renovated. It protects against the cold in the next season. What then? My model will still be valid or not? So in the open loop control, we are not able to compensate disturbances because all those things are disturbances. So they affect the output, but we do not have control over them. Of course, I have control over the fact if I'm opening or closing the window, but let's say my wife will come and open the window, right? So as every husband understands, we don't have any kind of control over our wife, so it's a disturbance. Greetings to Ivona. What can we do to compensate those disturbances? You can think of this. I will just mention that generally those disturbances results from some auxiliary factors, some plant modifications as well, right? Or the uncertainty related with the reality description, right? So this model, this is our description of the reality, it's not 100% accurate. There is some error, right? And of course, this error cannot be compensated in such an architecture. We should inform the controller what is the current value of the output, what is, let's say, the current temperature in this room, measured in the sensor that I have in my hand, let's say. So the controller knows if it's too high in comparison to the demand value or too low. And then he can decide what to do. Maybe open, maybe close, or maybe keep this particular level of the valve opening. In order to give the controller this information, what is the current output value, we need to change this architecture. Now we have the closed loop control approach, a very typical approach in the factory or in the plant, where we have this feedback loop. So now the controller sees the error, sees the difference between the demand value, we'll call it a set point, and the output value. Right? The goal of the controller is to minimize this error, is to keep it zero. So he changes the control signal. In our case, it's the valve opening level, but it could be, I don't know, the fan load, right? The feeder speed, etc., etc. In order to minimize this error. If some disturbance will occur, right? So somebody will open the window. Of course, this will affect the output. The temperature in this room will drop after a while, because this is also related with some process dynamics, right? So if somebody opens the window, I will not feel the temperature drop instantly. There is some transport delay and some inertia related with this process. So if the temperature will start to decrease, the error will start to rise, because we would like to have 22 centigrades, and it's not now 21, 20, 19 centigrades. So the error will increase, and the controller will take the action to change the control signal in order to decrease this error. So in this particular case, if the controller is well tuned, it will start to open the valve. Depending on how aggressive is the controller, it can open the valve immediately to 100%, or he can be more gentle. He can start opening the valve gently. So it depends on how we will define it. So the closed loop system is able to stabilize an output signal on a set point value, even in case of disturbances. The obvious advantages of the closed loop over the open loop approach is that the disturbance impact on the plant is limited, and also the impact of plant parameters modifications is limited. If I will change my devices in my plant, I will renovate the process, the characteristics of the process will change, I will use different fuel in my boiler, etc., etc. The controller is able to compensate it. All right. So what is the algorithm that defines this controller? It can be any kind of an algorithm, but the most popular one is the PID controller. You will find it in every factory and every plant. This is an absolute standard in industry. All right, so we should not invent the wheel. We have this PID controller, we can use it. So this PID controller consists of three terms: the proportional term, the integral term, and the derivative term. That is why it is called PID, proportional integral derivative. If there is no D term, we will call it a PI controller. If there is no I, we will call it a PD controller. All right? Usually when we say there are PID controllers on the plant, but usually those are the PI controllers without this D part, without this derivative term, and we will discuss later on why we don't have this D term. So the general equation for the PID controller is this one. So the control signal is the error signal multiplied by the controller gain, but also, so this is the input signal, this is the controller gain, but also we have the integral term where we are summing the historical error values, and we are acting proportional to the value of this sum. So if the temperature in my room is rising above this 22 centigrades, so it's 23, 24, the sum of error, even if it's constantly 23, right? And I will take the error measured, I know, every second. I will see that the sum of this errors is rising. The error hill is higher and higher. So the reaction of the controller, the value of this output signal will be proportionally higher to if the sum of these errors is also high. So here we are reacting proportionally to the sum. Here we are reacting proportionally to the current value of the error, right? So on the one hand, we are looking what is the situation right now, here and now. And on the other hand, we are looking to the past and thinking, maybe we are too gentle, maybe we should push more, because if you take a look on the history, we can see that we are in average or below or above the set point. In case of the derivative term, we try to, let's say, predict what would be the value of the error. So we are observing the changes of the error. If the error is rising, right? So it means if the error is rising, so it means that temperature is dropping. we will assume, oh my gosh, it's going down, we should do something, right? So the output signal value is proportional to those changes. And of course, we can decide what is the weight related with each term, what is the gain of each term. So in case of the integral term, this gain is expressed by 1 divided by by integral time. This t is integral time, t. And here this td, this is the derivative time, this is the gain of the derivative term. So if we will set, I don't know, integral time to infinitive, then it means that the gain of the integral term is 0. So we don't want to look into the past, we just want to react to the current situation, right? It will be then the P controller or PD controller if the TD value is higher than 0. And of course, we can open the in the distributed control system, we can open the control sheet, click on the controller algorithm, and we can check what are the weights related with each term and what is the nature of this controller. This is, of course, the continuous form. If you would like to implement something in the computer, right, we need to have the discrete form of the algorithm. So this is the very, very simple discrete form of the controller. Usually we are not implementing the derivative term this way, but I just want to show you this this very simple equation just to understand the operation of the controller, right? So we have this sum here, you have this error difference. Yeah. So here you can see the general idea. We have this demand value, the set point, it is compared with the output, the error is calculated, and then there is a gain that increases or decreases the value of this signal, and part of this signal goes directly here and makes the control signal. So this is the reaction for the current value of the error. Part of this signal is integrated, right? And the part of the control signal reaction is proportional to the value of this integration, to the sum of errors, to the fact that the previous errors was rather positive or negative. And we have also this derivative term where the part of the control signals, this is the reaction for the derivative of the error signal. So we are trying to see where it's going, right? To react for the things that will be in the future. And of course, if we are implementing the AI method that, I don't know, optimizes the plant or the factory, it usually changes the set points. So the AI algorithm usually changes the set point for the temperature, the set point for the flow, the set point for the device load, not the control signal itself. So not the valve opening level, right? Not the feeder speed, etc., etc. Rather, not the, maybe the feeder. It depends, of course. But we prefer to change the set point in our AI algorithm instead of affecting devices directly. Because, well, all the work will be done by the PID controller, by the control system. We are only asking for high temperature, and the control system, which is hopefully well tuned, it has to be checked before the project, will take the output temperature to this desired level defined by our AI algorithm. It's better than deciding about the load of the about the flow of the water, hot water that enters the radiator, right? So we don't have to think about details, how it is done in the plant. We can focus on the value of parameters. But of course, this is a very simple case. Usually those control systems are more complex. I will show you this. So always we have to think where to send our AI algorithm decision. Where should we implement the hook? Now I would like you to have a feeling of what is the PID controller. So let's start with the very simple example with just the P controller. So as you remember, the P controller has only gain. The D term is missing. The T term is missing. The integral term is missing. They have gain equals 0. So we have only this part. Now the output, the control signal, is the error signal multiplied by some gain. So let's try to analyze the system. And of course this controller is connected to the plant. If we change the set point from 0 to 1, this is so-called a step change of the set point, we will increase the value of the control signal, because you see the output of our plant is here. Let's say let it be this temperature, right? But the set point changed to 1, so the error is 1 minus 0, 1, and the PID controller reaction is proportional to the error signal, the current value of the error signal. So if the gain is 0.25, the control signal value will be 0.25. After a while, after a time that is defined by the transport delay of the plant output starts to change, starts to increase. The error is decreasing, right? Because the plant output is increasing, is getting closer and closer to our set point, so the error is decreasing. If the error is decreasing, then the control signal is also decreasing. So the reaction of the plant is also getting lower and lower, right? We are sending less and less energy to the plant, so the plant output is still rising, but not so fast. And because of this, the error is also changing but slower. It's decreasing but slower. So the control signal is also getting down, etc., etc. On the end, we see that the output of our plant stabilizes here, and it is unfortunately below the set point. All right, so also the control signal is stable, everything is stable, but we are not able to reach our set point. What can we do? We can at least try to increase the gain, just to check what will happen. Here you can see that right now the set point was once again changed from 0 to 1, so we have this step change. The gain is 1.5, so it's essentially higher than in the previous example where it was 0.25. So the error at the beginning is 1 because of the process dynamics, right? The plant output haven't responded yet. So the control signal is really high. We are sending a lot of energy to the plant. We are kicking the plant. We are saying, "Hello, wake up, buddy! Time to work." And because of this, after the time defined by the process transport delay, the output of the process starts to rise very fast. This is a fast change because we sent a lot of energy to the plant. On the other hand, the error is decreasing. So when the error is decreasing, the control signal is also decreasing proportionally to the error. This is this black signal, right? So the output is stops to increase. After a while, the error is even lower than 0. So the control signal is negative. Now we are saying, whoa, stop, not so fast. We are pressing the brake pedal, right? So after a while, this time is related with transport delay and process inertia, the process output starts to decrease. It's going even below the set point. So if it's going below the set point, the error is increasing. It's getting positive values. The control signal right now also have positive values. So now we are pressing the throttle pedal, right? And then we see that so we are sending more and more energy to the plant. So after a while, the output value is increasing, is even higher than the set point. So we have to really press the brake pedal and send the negative values to the plant of the control signal. So we are oscillating this way until we reach the new steady state, which is here. So it's better than the previous example. We are closer to the set point, but still not on the set point, right? We are sending more energy to the plant in the steady state here, but still not enough. So what is the problem, right? What can we do? Well, we can try to even increase the gain of the control even higher. But it's very risky. So even right now, those oscillations of the control signals are very bad. We don't want to have such signals in the plant because we can destroy the actuator. In this particular case, I don't know, the valve that controls the water flow to the radiator, to the heater, or I know the engine of the engine or the damper. So we have to be gentle while playing with our devices, right? But suppose that we have a chance to check what will happen if we will increase the gain. In this particular case, the closed loop system is not stable anymore, right? So the amplitude of those oscillations are bigger and bigger over time. So we should really avoid such situations. Those situations are very dangerous, and there should be no such cases in reality. So, what to do? What is missing here, right? From time to time, we are above the set point. For most of time, from the majority of time, we are below the set point. So we should somehow tell the controller that, okay, he was reacting to the current value of the error, but if you look at the history, we can see that we sent not enough energy to the plant, right? Not enough energy to reach the set point. So we should increase the value of the gain of the integral term, and in fact we should have the PI controller, the controller that has this integral term. Let's take a look on how it works. The set point changed from 0 to 1, as in the previous example, and of course the error changes from 0 to 1 as well, but the control signal looks different. So on the one hand, we are reacting to the current value of the error, and this is the output of this P term, proportional term. This one, if the set point, the error is 1, and the gain of the controller is here, is 0.855. So the value of the control signal is here, but due to the fact that over time this error stays on the same level, it's 1 in the first second, it's 1 in the next second. So if you take the sum of errors after those 2 seconds, you will have 2. In the next second, error still is 1. So the error hill, as I call it, now is 3. That is why the reaction of the I term, integral term, is this one. So we see that the error is not moving, so we have to send more energy. So first, so this is this reaction, that is the sum of the proportional term output and the integral term output. This is the final value of the control signal. First, we kick the plant, we say wake up, then we see that, well, the output is still sleeping, so we have to start to sense more energy, right? And after a while, plant response, we see the plant response, the temperature starts to rise, the error drops, the proportional term output also is decreasing proportionally to the error signal, to the current value of the error signal, but the error is still positive, right? It's lower than 1, but still it's positive. So the error hill is still rising. The sum of historical errors is still rising. So on the one hand, we are pressing the brake pedal. We say, oh, it's definitely less energy is needed because we see the output response. But on the other hand, the I term says, no, let's add some more energy still because we haven't reached the set point yet. And the final value of the control signal, this is the compromise between those two. When the output signal reaches the set point, the error is 0, so the control signal proportional to the error value, this P term output becomes negative from now on. So we're really pushing the brake pedal. But the I term is still, the I term output is still positive. Of course, this error hill decreases because we are adding negative values of errors, but still it's above 0. Still it's quite high. So still we are saying, okay, despite the fact that now we are above the set point, in the past we was below the set point for a long time, so we should still send some energy to the plant, because maybe this is temporary. And then, because of this brake pedal pressing, because of decreasing this control signal related with the reaction to the current value of the error, the process output is also decreasing, but not so much as in the previous case, as in the previous example without this I term. The I term keeps this energy that is sent to the plant on some level. So this bump is lower than before, and because of this, that proportional reaction can be limited, right? We can more rely on this integral reaction. We can be more gentle, and you see that over time we are able to reach the new steady state, where the output of our process equals the set point. So we reached our goal. We was able to change the temperature in the room, or change the pressure, or change the flow of the air, of the water, etc., etc. And of course, if the error is zero, then the proportional term output is also zero, right? So there is no error. We don't have to react for the current value of the error because it's zero. But on the other hand, we see that there is some portion of energy needed to be sent to the plant in order to keep this value of the output on the set point, and it is defined by the I term, or by the integral term. Of course, we can have different settings of those gains and integral time. So the integral time is 1 divided by the integral time. This is the gain of the I term. We can have such a setup, right, where this is the same case. We have changed the set point from 0 to 1, but the reaction of the proportional term is lower than before. So still it's, hey, wake up, cool, wake up, buddy, but it's more gentle. It's not so aggressive, right? The integral term is more aggressive here. Yeah, if we see that the error is not moving, the error here is rising, we are more rely on the past than on the current value of the error. So we have such a very smooth transition. We are reaching the set point without any bumps, any oscillations, right? So in this approach, we reach the set point slower. We need more time to reach the set point, but there is no bumps, no oscillations. We are not above the set point. So this is the control signal is much more gentle. This approach is better for the cases where the accuracy is important, but not the time. The time is less important. If we are filling the tank, we would like to fill it to 100%, but we don't want to see our water flying out of the tank. While here, we can reach our set point faster, but of course there are some bumps, there are some deviations from the set point, but if we can accept them, maybe this is the better approach. We can accept them if this is, I don't know, the pressure, the temperature. Why not? Some deviations are possible. Okay, so one can say that in this particular case, if we compare this controller to just the P controller, the controller that has only the gain, we can say that such a controller, in such a PI controller, the P term has a smaller rise for proportional reacting for the current value of the error, but the I term supervises the efficiency of the P term operation and additionally modifies the control signal in order to compensate integrated error that results from the weakness of a P term. So, integral terms, we can say it sees that despite some oscillations, an average value of the error is not equal to 0. So, the I term is able to bring this difference to 0. That is why usually on the plants we will have PI controllers. Why not PID controllers? Why usually? Because sometimes you can have this D term as well. But we rather avoid this D term in the plants. Adding this D term means that we are trying to forecast what will happen with the error. If we see that the error is rising, we will say, oh my gosh, the error is rising, it will be maybe infinitive in the next minutes, so we have to do something with this, right? We need to add more energy now because it will be a disaster in the nearest future. Of course, it will happen like this only if we will set a very aggressive gain of this D term. But I would like to, explain this topic to you so you can understand why we should avoid this in the plants. So, of course, adding the D term means that we can have a faster reaction. We can get our process output to the set point faster because we can forecast the future value of the error. But there is a risk of system destabilization, especially if there are noises, and usually there are noises. So all the signals are related with some measurement noise. And if the controller will react to those noises, it would be something really bad. Because, what are those noises? Suddenly the process output rises, then drops, then rises, drops. So this is the noise, right? So if, because of the noise, the process output will rise, then the error will drop, right? So the D term will say, okay, so it's dropping, so it would be 0 or even negative in the nearest future. So I should immediately stop sending the energy to the plant. So it will close the valve, right? It will decrease the engine load, etc., etc. On the other hand, if in the next second, because of the noises, the error will rise, then the D term will ask for more energy to open the valve, to increase the load of the engine, and it's not a good behavior, right? It can destabilize the process. It can change it can damage the actuator. So in case of plants that are characterized by high process dynamics, by long transport delay, high inertia, this D term is not so important, and rather we try to avoid this. It's not bad. This D term is very good, but usually for different purposes. If you have a robot that try to walk, right? If it start to fall, it needs to immediately react to this. It needs to have this projection that the error, the deviation from the vertical position to the horizontal position, right? This error will increase. So I have to do really something to get my position to the vertical one as soon as possible. The accuracy is not so important. Maybe I should, if I'm falling on the right side, maybe as a robot I should move my left hand here in order to stabilize my position. I don't have to be exactly the vertical position, right? But I have to act fast. Then this D term is very, very important. But usually it's not the case in case of plants. Okay. Right now we was talking only about set point changes. But as you remember, we are using this closed loop system mainly to compensate disturbances. Of course, we have to react to set points, we have to react to set point changes, but also we have to, the control loop has to react for disturbance changes. So if the disturbance will change and when it affects the output, we will see the change in the error, right? And of course, in such a case, the PID controller will react in order to minimize this error. Here you can see the disturbance tracked output. So this is this signal. It increases the output of our plant, but on the other hand, controller reacts to this, right? And tries to get the error back to 0. All right, so we can have more than one form, one more definition of the PID controller. So far we was talking about the standard form of the PID controller, but we can have different implementations, parallel, serial implementation. Usually there is a real derivative term instead of ideal derivative term that was presented in the slides. So we should always check the manual of the control system and check what is the definition of the PID controller before we start playing with it. It's easy to, switch from one form to another, but we should check what is the form in this particular distributed control system, in this particular PLC controller. This is, for instance, the example of the PID controller that is defined in the Ovation system, the DCS system that is usually that is present in power plants, for instance. So in this particular case, this gain that in standard form was here is moved here, right? So the error that enters the integral term is not multiplied by gain anymore. We have to remember about this. Okay, and what is the the real form of the derivative term? You can see it's this is, let's say, the ideal derivative term as I was presenting plus some inertia. So it's filtered, right? In order to prevent some historical decisions that are, for instance, based on the process noises associated with process parameters. Okay, now we know what is the PID controller. Let's take a look on how it is implemented in the DCS or a PLC, and what is the tracking. If you take a look on the implementation of such a control loop in the DCS system, it will usually look something like this, more or less. You'll have the PID controller. It will have usually two inputs. One would be the set point, and one would be the process value, the output of this parameter that is it should be on the set point, right? Then we will have the control signal and the device, the symbol that represents the device. In the middle, somewhere, you will have the manual auto station, where the operator can switch from automatic mode to manual mode. This set point usually, in a complex systems, this set point is the function of our other signals. Like, for example, we have some function, some characteristic that calculates what should be the set point for the current unit load, for instance, for some main signal, right? Usually it can be biased by the operator, so the operator can add something to this signal, can increase or decrease this set point a bit. Okay, here we can also send the decisions from our AI algorithm, so that there is some if-else algorithm with a flag. So if the operator press the go ahead AI algorithm, you can control the plant. The AI algorithm will define what is the set point. However, if the operator will press the off button, then the AI algorithm should observe and track the decisions of the control system. So the set point will be calculated in, let's say, the normal way. However, if the operator will switch to the manual mode here, right? So he has set the operator graphic, he can click on the device and say, right now I will control this fan, right now I will control this engine, right now I will control this valve in the manual mode. In such a case, the control signal cannot be sent to the device from the PID controller, because the operator defines what is the value that should be sent to the device. So usually the PID controller in such a case should track the operator decisions. So we define tracking in the DCS. In such a case, if we will define tracking between the manual auto station and the PID controller, the inner state of the controller is constantly recalculated in such way that the output of the controller is equal to the operator setting. And of course, the anti-wind-up protection is activated, so the error is not integrated. I will not talk about the anti-wind-up. If you like to hear about the anti-wind-up protection, then write me a comment and I will make a video about this. Usually we define the tracking to the set point. So if we will define tracking in such way, the set point value will be recalculated in such way that when we compare the new value of the set point with the current measured value, on the output of the controller, we will have the value that is equal to operator decision. Right? We can send this tracking even higher to the operator bias. So in this case, the operator bias is recalculated in such way that if we compare it, if we add this new operator bias value to the set point signal calculated based on some characteristic, based on some other important process parameters, we will have such set point value that when we compare this set point value with the measured value, we will have such the PID controller output that is equal to operator decision. Why I would like to have it? Because if we will switch back to auto mode, we don't want this transition should be bumpless, should be smooth. We would like to start in the same place where the operator has finished his decision, right? We would like to have the same process state. We don't want to suddenly change the control signal by 50% like this, right? And the same refer to the AI algorithm. I will talk about this in the next video. We should also track our AI algorithm should also track the operator decisions, because if the operator will say that I switch to auto mode and I press the start button, so now dear AI algorithm, you can supervise particular devices, you have the full control of those devices, we should be able to send the proper value of the set point. That will be it should be the bumpless transition. We should start in a process state where the operator has finished his manual mode, let's say. So now let's talk about the feed-forward control. Let's talk about compensating the disturbances in the open loop. This is a very popular, is it a good word? It's better to say it's a standard approach in plants to compensate disturbances in this way. So let's go back to this example with the radiator in the room. Now suppose that the radiator is here close to me. Oh, well, it's even here. This is the proof, the radiator. So, and the window is in the opposite corner of the room. So, as you remember, if someone opens the window, this is the disturbance for me. I have a PID controller in my head, and this PID controller would like to keep the temperature on the set point. We said that the set point is 22 centigrades. So if someone opens the window and right now it's 0 centigrades outside, the temperature will drop. So let us also assume that the transport delay on the disturbance track is 2 minutes. So if someone opens the window, I will see the temperature drop on my sensor after 2 minutes. After 2 minutes, temperature will start to decrease and it will reach a new steady state after a while, related with process inertia. Okay, so in such a case, my PID controller in my head will send a control signal to my hand that will change the valve position in this radiator over here. So if this is a radiator supplied by the hot water, of course there is a valve. If I open this valve, the more hot water will enter the radiator, the more heat will be generated, will be transferred to my room. In the case of the radiator that I have shown you, this is the electrical radiator, so there is also some kind of a control functions of this radiator. I can set the level heating in this radiator. So I will increase this level here, right? Because someone opens the window, I would like to have 22 centigrade, so I will increase this level. So after 2 minutes, the temperature will start to decrease. I will open the, I will increase the heat level in this radiator, and after, let's say, 30 seconds, this is the transport delay on the control track. After 30 seconds, I will see that the temperature stops to decrease and starts to increase. And of course, my P and I and maybe D term will try to find such level of this heat generation setting that will stabilize the temperature on 22 centigrade. The question is, can I change something in my control strategy in order not to see this temperature bump? So even if someone opens the window, I will have this 22 centigrade all the time. This is the goal of the feed-forward control. So the idea is that if I know that someone opens the window, so the disturbances has been changed, and the transport delay in this disturbance track is 2 minutes, and on the other hand, I have this radiator here, I have a plant, and the control track delay is half a minute. It's obvious that I don't have to wait to see the temperature drop. If I can measure the disturbance, so right now I measure it with my eyes, that someone opens the window, then I can act faster before the disturbance affects the output, right? So there is 2 minutes there, 30 seconds here. So after 1.5 minutes, I will start to increase the heating level in this radiator, right? So because 30 seconds is enough to see the reaction on the output. I will try to find such level of this setting, heat generation setting, that will ideally compensate the effect of the disturbance. So what I have to know, I need to know what is the model of the impact of the disturbance on the temperature. So I need to model the disturbance track, not only dynamics, but of course mainly the gain, so static relations, and I also have to have a model, a transfer function, if you like to refer to things that we are using in the control theory, or the differential equation, because this is transfer function is another representation of a differential equation that represents the impact of changing the settings here in this radiator on the temperature. I have those two models. I know when to react and how fast, and such open loop disturbance compensation is the feed-forward control. So this is our standard approach, right? The control loop with the feedback. But here, after the controller, we are adding the feed-forward block, feed-forward algorithm, that based on the measured disturbance, it is calculating corrections of the control signal. And this calculation is based on the disturbance track model and the control track model. In fact, if we divide the transfer function of the disturbance by the transfer function of the plan of the control track, and if we add the minus, we will have the equation of the feed-forward algorithm. This is very useful. And in fact, what we want to do in the AI algorithms, what we want to do using predictive models, in fact, we would like to compensate disturbances in the optimal way, predicting what will happen in the future. So we can say we are developing much more complex, much more sophisticated feed-forward modules. All right. Now let's try to change our arrangement in the room. Now the window is, let's say, here. Let's pretend that there is a window, and the radiator is on the other corner of the room. So now, if someone opens the window, I will feel it. I will see it on my sensor, temperature sensor, after 30 seconds. I will see the reaction. So the disturbance tracked delay is 30 seconds. On the other hand, the radiator supplied by the hot water is on the other corner of the room. So now the control track transport delay is 2 minutes. In such a case, I'm not able to ideally compensate the disturbance. After 30 seconds, the temperature will start to decrease. But of course, I should not wait 30 seconds, right? I should immediately increase the valve of the hot water associated with the radiator in that corner of the room. Immediately. Of course, there will be a temperature drop, but it will be this temperature drop will be smaller than in comparison with the standard approach without feed-forward control. And of course, feed-forward modules are not ideal. So we need this controller to compensate errors of this model, right? Moreover, if someone changes the set point, of course the controller has to do his job. So we need the controller, and it's good if we have this feed-forward module as well. Okay, I will skip it. I hope you get the idea. Now the linearization. So sometimes within the distributed control system with the control sheets, you will find linearization blocks. Of course, in the plant we have nonlinear processes, like for instance this one, right? So it could be, let's say, the airflow through the air damper, or water flow through the valve. If we open this damper from 0 to, I don't know, 10%, we will see a huge increase of the airflow, right? But if we open the valve from 90% to 100%, there will be nearly no change of the airflow, maybe very slight change of the airflow. This is this nonlinearity. We change the valve by 10% here, and we saw a huge reaction of the airflow. But if we change the airflow by 10% here on the right edge of the domain, this reaction will be very gentle. PID controllers do not like such processes, right? The PID controller is tuned for specific operating point, maybe this one, maybe this one, maybe we have a different seconding for this point or for this point, or maybe it's some kind of compromise between different points, but it has one algorithm, and it assumes the reality is linear. So it assumes the plant will react in the same way every time we change the control signal by X%. So in order to get rid of this nonlinearity, we can add a dedicated algorithm in the control system that is responsible for linearization, like this one. Right? So this is a plant, but this is a part of our control system. We can add such a module that is symmetrical to the plant characteristic. And if we know that the plant reaction is very aggressive, if we have low values of damper opening, we need to somehow artificially decrease the control signal in order to have a linear characteristic of the final plant that consists of the real plant and our linearization module. The same here, if we know that the reaction of the plant is very gentle when we have high opening levels of the damper, we have to add some gain. We have to increase this control signal in order to see the reaction that is more or less linear from the controller point of view. I'm talking about this because you have to treat the plant and the control system as one big plant, one entity, one process, one system. That if you try to develop a predictive model, a digital twin, some AI algorithms that helps to run the plant. Because if we just take the characteristic of a device, we will see it's non-linear, and we'll try to somehow handle this non-linearity in our model. Probably it won't be a good solution. We have to consider this control signal, because this device is operating under the supervision of the control system. So if we have this linearization module, then we can treat the process as linear. Of course, I will talk about the cascade control. The inner control loops also makes the linearization of the plant. Let's take a look on the cascade control in order to discuss this topic. So let's start from the example. I think it would be the easiest way to explain the cascade control. Also a standard approach in the control system. So let us assume that we have a power plant, and in this power plant we have superheaters and reheaters. We will focus only on superheaters. What are those superheaters? Those are heat exchangers. So the steam is going through those pipes. We have a lot of pipes here, and here we have hot gases from the combustion chamber, and there is a heat transfer from those hot gases to the steam in those superheaters. So the more hot gases flies here, the more the higher heat transfer. And of course, the higher heat transfer, the higher the temperature on the outlet of the superheater. Let us focus on the final superheater, probably is this one. But I'm not sure, so let us pretend that this is the final section of superheaters. The steam from here is entering the turbine, right? So it has some parameters depending on the boiler type. If we have a boiler with a drum, it's not this one, but if we have a boiler with a drum, a typical 200 megawatt unit, it would be 540 centigrades, right? And a high pressure. Once again, depending on the type of the boiler, 15 megapascals, 20 to up to 25 megapascals. So, but let's focus on this temperature. We would like to have this 540 centigrades at the outlet of the superheater here. So before the turbine, we would like to have 540 centigrades. The higher the better, the better efficiency of the process. But if it's too high, we can, destroy those pipes, right? So we are risking. We will, if the temperature will be too high, like 550, 560, we'll see alarms related with the heating surfaces that the temperature is too high and it can damage the boiler. On the other hand, if it's too low, the efficiency drops. So 540 it's let's say the optimal temperature for drum boiler with a drum. It's of course higher for supercritical boilers. And how we can control this temperature? We can inject cooling water into the pipe with a steam. Unfortunately, we have to inject this water before the superheater, because if we inject the water after the superheater before the turbine, the water can damage the blades of the turbine. And those droplets of the water can destroy the blades of the turbine. So we have to inject this water before the superheater, which is problematic from the control system point of view, because the superheater, you see how many pipes is here. It's a big heat exchanger characterized by essential transport delay, like 30 seconds, a minute, and some inertia. So if we will, for instance, inject too much water, cold water into the pipe, we will see the reaction of the temperature after a minute, let's say. After a minute, we'll see that, we injected too much cold water. So we will increase the cooling water cooling water flow. And we will see the reaction after a minute and we'll see, no, it was too much. So it's hard to control this process. On the other hand, this T1 temperature, the temperature that is measured just after this injection, reacts to the cooling water flow very fast. The transport delay is measured in seconds. So after a few seconds, we can see the temperature decreasing if we inject more cooling water, or increasing if we will close the valve. So if we would like to control this temperature before the superheater, we can have a very fast and accurate control loop. But with this one, it's harder. It's much harder. We will need to have a more gentle, slower control loop. So the quality of this T2 control system, the quality of this system would be low. So maybe the optimal solution would be to have two control loops. Let's take a look. We can add a primary controller that of course we need this primary controller to keep this final superheat steam temperature on desired level. Let's say this 540 centigrades. But this primary controller, let's say the gentle one, slower one, less aggressive, will, because of the high process dynamics here, will not control the cooling water spray directly, because it's hard. Moreover, you know, I haven't mentioned this, but the characteristic of this cooling water injection is non-linear, right? So if the controller assumes that the reality is linear, so if it's not linear, we will see that we add too much or not enough cooling water after a minute. So it's too late, right? It's hard to control such a process with big inertia using the device that has a nonlinear characteristic. So this primary PI controller is calculating not the cooling water flow, but the demand, the set point for this T1 temperature, the temperature that is just after the cooling water spray. And in such configuration, the secondary PI controller tries to keep this T1 temperature on the desired level. Right? So this is a fast control loop, a fast aggressive controller that can really set this T1 temperature to the get this T1 temperature to the set point in seconds. And we have this this slower control loop where the primary PI controller calculates the demand, the set point for the secondary PI controller. This is a cascade control. Please take a look that from the primary controller point of view, this inner control loop makes the linearization of this spray injection, which is non-linear, right? This guy don't have to worry about how this T1 temperature will be reached. He just asked for a particular temperature, and this guy here will do his job. Will take this T1 temperature to the set point. If the secondary PI controller will add too much water because of nonlinearity, we added too much water, we will be able to compensate it in a seconds, right? So the plant looks linear from the primary controller point of view, where the plant is the real plant plus the inner control system. In fact, what we are doing while implementing AI algorithms, we are adding another layers of the decision strategies, right? So for instance, if we would like to make a model that tries to find an optimal final superheat steam temperature, we would not calculate what should be the cooling water spray injection, right? We would not even calculate what should be the T1 temperature. We would rather calculate what should be the set point for this T2, and we will assume that the primary controller and the secondary controller will do their job, will handle it. Of course, if we will calculate the set point that is reachable, that is possible to realize. Because, for instance, if we have a low unit load, we might not be able to reach this 540 centigrades, especially if we are using the poor quality fuel. And here you can see the feed-forward correction, right? So we can also use the feed-forward correction. Why not? If we know that there is a unit load change, if we know that after in the next 15 minutes the unit load will change from 180 to 200 megawatts, we can assume that we will see this, so we'll produce more hot steam, right? So the temperature T1 will increase, and after a minute T2 will also increase. So if we know what is the disturbance tract model, disturbance tract transfer function, so what is the transport delay between changing the unit load and the T2 reaction, what is the gain, right? What is the inertia? And also, if we know what is the T2 reaction for our T1 set point temperature change, we can do the feed-forward model. And in fact, we are implementing such things. So to summarize it a bit, oh, well, by the way, here you can see the part of the real control system where you have one PID controller that calculates the set point for the secondary PID controller, right? This is how it looks in the memory of the controller. And this is the operator graphic, where the operator, this is a supercritical boiler, so those temperatures are higher. The operator can see, maybe, I don't know if it's supercritical or not, but for sure it's one through boiler without the drum. The temperatures are higher, so here you can see this 560 centigrades. Oh, and you remember my last video about the fact that in this DCS control, in the DCS system, you don't only see the values, but also you see the quality of the measurement. Here is such case. You can see the valve is open to 30%, but the system, the DCS system, do not trust this value. That is why he add the bad quality indicator. All right, so once again, the cascade control is the approach where you have at least 2 control loops, but you of course can have more. The inner control loop controls some kind of a sub-process and helps to linearize the plant from the primary controller perspective. It's much faster. Usually it's like 10 times faster than the primary controller. And there is a main process that we would like to control. And primary controller calculates the set point for the secondary controller. So he do not affect the actuators directly. He calculates the set points for the inner loop. And this is important because when we try to understand the system behavior, because we have to do, the predictive model of the plant, we need to understand those control loops, feed-forward modules, and we have to consider the whole system as devices plus the control system. And the question is, if we would like to have the automatic control over the plant or part of the plant with the utilization of our AI algorithm, we need to decide where to place our hook, where to send the decision. Should we calculate the set point for the primary controller or the secondary controller? It's every time we have to think about this. Okay, and that's it for today. I hope that right now you know what is the PID controller, what is the control loop, what is the feed-forward control and the cascade control, what is tracking, what is linearization. Those are important things. And you know that those algorithms are executed in controllers, and controllers are part of the distributed control system or a set of PLCs, right? Plus SCADA system. So I think you have all the bricks to start a new video about integration of the AI algorithm within the control system. I will talk about this in the next video. Thank you and have a good day.